Okay, welcome back. And today we're going to start chapter 8. And so we're going to continue on with our topics of probability. And we're going to go one step further because now we're going to start dealing with things that are going to be a little bit more complicated that we can't count. Like up until this point, we've been dealing with sets of objects, sample spaces that we were able to actually be able to count things, and then we were using uh, the definition of probability to just plug and chug and divide. And so we always knew what number, we could always count and figure out what number goes on top and what number goes on the bottom when we calculate probabilities. Well, in a lot of cases, in many cases, that is either very difficult, impractical, or impossible to do. So what this chapter is all about is how do we figure out what number goes on top and what number goes on bottom of calculating a probability when it is more complicated to count, or we just can't count them because we're dealing with millions, hundreds of thousands, or tens of thousands, even hundreds. Okay, even more than 75 or 50, right? We're not going to want to do that. We're not going to want to sit there and write out 50 different possible outcomes if we're talking about the number of ways that we could have 5 babies and we're looking at gender, right? So that would just be too much to write down, right? Um, and we don't want to do that. So this chapter is all about, okay, how do we easily and quickly figure out what those numbers are? What are the possible outcomes that give me a particular event? What are the total possible outcomes in a sample space or in a probability experiment? So in this chapter, we're going to say, okay, how do we figure out what those are when the numbers are really big, and how do we do it quickly? So the first section is going to be introducing you to the fundamental counting principle or the multiplication principle and permutations. So in this case here, the fundamental counting principle, or what they call the multiplication principle, says that we have n choices. So let's say we're choosing n distinct objects. Okay, so n choices means that, hey, I'm going to choose one from one category. So let's say I have n categories, and I'm going to make one choice for each category. And so in category 1, I can choose one item, and let's say there's M1 different things in there, okay? Or M1 objects in there. And in the second category, I have M2, and so on and so forth, all the way to M sub n. And so I'm going to choose one from these n categories. What that means is if I want to know how many different ways can I make a sequence of choices, right? So how many different ways can I choose things, one item from each one of these? Okay, so how many different sequences can I have? Well, the answer is the fundamental counting principle says take all of the different ways that you could choose from each one of the n categories and multiply them together. That's it. And the answer will give you the total number of sequences you can have, the total number of ways you can choose those distinct objects. And so in this case here, we're looking at, let's say you go to breakfast. And so this is how the counting principle works with the tree diagram, okay? So the counting principle says, okay, I can either have a bagel, a muffin, or a donut, okay? And I can either have coffee or juice, right? So I can either have choose something to eat, and I could choose something to drink. Of the things I can choose to eat, I can choose only one of either a bagel, muffin, or donut. Okay. And then for a beverage, I have a choice of coffee or juice. So the question then becomes, okay, well, how many different combinations, or excuse me, I don't want to use that word yet. How many different ways can I choose one thing to eat, one breakfast meal, and one drink? Or in other words, how many different meals can I create if I put one of those things I'm going to eat, something to eat with something to drink? Okay, and the counting principle says, well, How many different items are there to choose from to eat? Well, in this case, 3. How many different items are there to drink that I can choose from? Well, in this case, 2. Well, then the fundamental counting principle says, well, just multiply those two numbers together. So 3 times 2 gives 6. So there should be 6 total different meals that I can create. Well, how do I actually see what they are? Well, you can use the tree diagram here. So if you use the tree diagram, so the first branch is what you're going to eat. So you can choose one of these. And then after you choose one of these, you can choose something to drink. And so your choice is either going to be coffee or juice. So if I go down each branch of the tree, that will give me one outcome, one meal, one sequence. Okay, so I could have a bagel with a coffee, or I could have a bagel with a juice, or I could have a muffin with a coffee, or a muffin with a juice, or a donut with a coffee, or a donut with a juice. So that gives me all 6 of the outcomes. Okay. Now the fundamental counting principles gives me the number. The tree diagram, you can not only gives you the number, but you can see what those outcomes are. Okay. So again, very good tool to use for visualization. Okay. Not so good when you get more and more choices. Okay. So what if I said, went to dinner and I said, okay, you can choose an appetizer and you can choose something, your main meal, and then something to eat for dessert, right? Well, what if there are 6 appetizers to choose from, 7 main meals to choose from, and 5 desserts? Well, in that case, your tree diagram is going to be pretty messy. So again, you're just not going to want to use the tree diagram all the time, okay? It won't be practical. But anyway, it's a good thing to start with so you can see what's going on and prove to yourself how the counting principle works. Okay, now here's a combination lock. So a combination lock can be set to open to any 4-digit sequence. Okay, so how many possible sequences are there then? Okay, how many possible sequences are? Well, if we were to write down all the possible sequences, that would take a long time. But if we use the fundamental counting principle, it'll be easy. Okay, because if we use the fundamental counting principle, how many things do we have? So here's what we're going to do, right? So we have 4 sequences, right? So here's the first number, second number, third number, fourth number. Okay. So now, how many numbers do I get to choose from for the first number, first digit, right? Well, these are numbers, right? How many digits do I get for the first number in the sequence? Well, I can have any number of 0 to 9. So there are 10. There are going to be 10 that I can choose from for this one, right? So I can choose a 0 to 9 for this position. Well, what about this one? Well, if we're talking about all possible sequences, then it's okay to have 1, 1, 1, 1, 1, right? Or 1, 1, 1, 1, okay? Or 2, 2, 2, 2. So we can have repeats, right? So we can have 10, 10, 9, 9, right? So we're going to allow for all repeats. So that means how many do I get for the second positions that if I allow for repeats? Well, that means I get 10. And how many choices do I get for the third digit? Well, I get 10. And how many do I get for the last digit? I get 10. And so now the fundamental counting principle says take each one of these and multiply them together. And so if I multiply them together, what do I get? I get 10,000. So there are 10,000 possible sequences for this combination lock. Okay. Now, B says how many sequences are possible if no digit is repeated. So we're not allowing for repeats. Okay. Well, what happens there? Well, let's draw our dashes for each position, right, of each digit, right, because we're talking about a sequence. So let's do our dashes. So again, how many choices do I get for the first digit? Well, since I haven't chosen anything, 10. Now, once I choose a digit, how many digits are left for the next position? So for example, if I choose a 9 for the first position, well, 9 can't be used anymore for any of the other 3, okay, because we're not allowing for repeats. So that means how many numbers are available, or how many digits are available after I choose the first one? Well, 1 less, which means now I have 9. And once I choose the ninth one of these 9, then for the next one, I've got 8. And then finally, for the last one, there are 7. And now if I want to know how many possible combinations are there, or how many sequences there are where there are no repeated characters or no repeated digits, then it's going to be this number. Okay? And whatever that number turns out to be. Okay, now, let me erase this for a second. Okay. Okay, so now notice here, right? So again, this is basically the same thing. So, and here's your number, 5,040. Okay, so if you allow for repeats, then you get all possible sequences, which is 10,000. If you don't allow for repeats, then you get 5,040 different sequences where there are no repeated digits. Okay. Now here, this is Morse code. So let's say we want to know, hey, how many different ways can I come up with Morse code? So Morse code is a sequence of symbols of you either have dots or you have dashes. And the sequence of dots and dashes make up words, okay, or letters. And then those string of dots and dashes will create a message, okay? So in this case here, we want to know, hey, how many different ways can I come up with, let me see, how many sequences are possible with at least, or excuse me, I'm sorry, at most 3 symbols, okay? So again, the question is given that we're dealing with Morse code with a series of dots and dashes, how many sequences of dots and dashes are possible with at most 3 symbols? So that means we want all possible sequences that are 3, all possible sequences involving 2, and all possible sequences involving 1. Okay. So if we do 1, well, if we do 1 symbol, well, how many choices do we get for 1 symbol? Well, we only get 2, a dot or a dash. So we only get 2 possible sequences. We either get 1 dot or we get 1 dash. Well, what if we have sequence of 2 symbols? Well, how many choices do we get for the first symbol? 2. How many choices do we get for the second one? 2. Well, 2 times 2 is 4. What if I take a string of 3 symbols? Well, how many choices do I get for the first one? 2. How many choices do I get for the second one? 2. How many choices do I get for the third one? 2. And so the fundamental kind principle says 2 times 2 times 2, and I get 8. And so now, so how many possible sequences are there that have at most 3 symbols? Well, then I'm just going to add these together. 8 plus 4 plus 2, which is 14. So the answer is 14. Okay, now let's talk about an ancient Chinese philosophical work called the I Ching, okay, which means Book of Changes. It's often used as an oracle from which people can seek and obtain advice. Now, the philosophy describes the duality of the universe in terms of two primary forces, yin, which is the passive, dark, receptive, and the yang, or yang, which is the active, light, and creative part. And so in this figure here, we have the two primary forces interacting with each other. Okay, so now, looking with this, okay, how many, okay, so if we look at the yin energy as a broken line and the yang energy as a solid line, then these lines are written on top of one another in groups of 3, known as a trigram. Okay, so when we look at trigrams, they're usually a broken line, which means we have a dash. Okay, so let me see here. Let me do it this way. Oops. So we can use it for the yin. Okay, so the traditional symbol for yin and yang, but the thing is the yin energy can be also represented as a broken line. So we can use this here. And the yang or yang can be written as a solid line. Okay, so those are symbols that we can use. Now these lines are written on top of each other in groups of 3 known as trigrams. And so for example, we could have something that looks like this. We could have a solid line like this with a broken line and a solid line like that. And this is called Tui. Okay, the joyous. Okay, and has the image of a lake. Okay, so now using this idea, the question is how many trigrams are there all together? How many different trigrams can I have? Well, remember, we're doing groups of 3, so we choose the top one, the middle one, and the bottom one. Well, how many choices do I get for the top one? I can either use what? A solid line or a broken line. So I get 2 choices for this one. So let's draw our dashes. So for the top line, how many choices do I get? I get 2. How many choices do I get for the second line? I get 2. How many choices do I get for the last line, the bottom one? I get 2. So the fundamental kind principle says there should be what? 8. 8 different trigrams. Okay, now, the trigrams are grouped together, one on top of another, okay, in pairs known as hexagrams. So what I can do is I could take 2 of these and stack them on as pairs on top of each other. And then each of those hexagrams represents one aspect of the I Ching philosophy. So now the question is, how many hexagrams are there? Well, if I have 2 of these, right, so there's 8 ways of doing this one, and then I do another one, right below it. And so how many ways of doing this one? Well, there's 8. Well, if there's 8 ways of doing this one and 8 ways of doing this one, well, then the fundamental kind principle says, well, How many different ways can I do both of them? Well, it'd be 8 times 8, okay, which gives me 64. Okay, and that's how the counting principle really works. Okay, so here's another one. So let's say we have a teacher is lining up 8 students for a spelling bee. How many different lineups are possible? Okay, this is a great question. Well, how do we do that? Well, let's do our dashes. Let's use the fundamental counting principle. So we got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so how many choices do we get for the first one? 8, right? For the spelling bee. So we got 1 out of the 8 we could choose from. And then after we choose the first one, well, they can't be the second one. Once you're the first, that's it. You can't be first and second. So that means we only have what? 7 people remaining to be second, 6 people remaining to be third, and so on. And so what happens is we get all the numbers from 8 to 1. And so the fundamental counting principle says, well, we're just going to multiply all of these together to find out how many different lineups of students that we can have. Okay, so now we can stick this into our calculator and find what the answer is going to be, right? So the fundamental counting principle will give us an answer. So let's figure out what this answer is going to be, right? So all we do is we do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and we get 13,444. 13,444. Let me just double check this. No, it's 40,320. So that's the answer. 40,320 different ways of lining people up for a spelling bee. Okay, now there is another way we could do this, and we're going to introduce a new symbol. And this new symbol oops, hold on. I hate this. Okay. Okay. So now here's the new symbol. This is called the factorial. So the factorial symbol is n factorial, or n with an exclamation point, but we say n factorial, and all it means is that it's an integer, right? We're talking about a natural number, so it's the numbers 1 through infinity, so it's all the whole numbers, integers, if you will, positive integers, and we use the fundamental counting principle, And it's all the definition of factorial is all we're doing is taking the first integer and we're multiplying by every successive integer down to 1. Okay, and so by definition though, 0 factorial is always equal to 1. Okay, so this is by construct and by pattern. Okay, so 0 factorial is 1, and then n factorial is basically n times n minus 1 all the way down to 1. Okay, just like we did in the last example. Okay, so now, suppose, excuse me, suppose the teacher in example 4, let me see here. So let's say we want, has 5 different books that he wishes to arrange side by side. How many different arrangements can be made? Well, just like the spelling bee one, well, if there's 5 books and you have 5 different arrangements, well, you could do what we did before. We could set up our dashes, right? We could do our 5 dashes, and then we could say, okay, well, how many books are there for the first position? 5, and then 4, and then 3, all the way down. Or we could just say, hey, well, since we know the factorial, then the answer is going to be 5 factorial. And so we can easily put that into our calculator and calculate it very quickly instead of doing it. So a lot of this stuff is going to be for ease of use. But also, when we get to the formulas, you'll know why we're introducing the factorial symbol. Also, one of the other things that I want to introduce or let you guys know about is that we can also, one of the properties of exponents is that we can, or not exponents, but factorials, is that we can write this, right? So we know what this means. This means 5 times 4 times 3 times 2 times 1, right? But we could also rewrite this as 5 times 4 factorial, right? Or we can write it as 5 times 4 times 3 factorial. So we can break it up, since it's just a product, we can always break it up into smaller and smaller pieces. Okay, so this is going to be something useful, okay, that we're going to want to use. Okay, so now, let's erase this before I go on. Okay, so now, permutations. So what is a permutation? Well, a permutation is when you're ordering objects, distinct objects in a sequence. And we're talking about choosing distinct objects where order matters. Okay, so the order in which you choose things matter. Okay, so again, if order matters, then we're dealing with permutations. Okay, now if we look at a couple examples here, and we say, what if I only wanted to, of the 5 books, let's say I only wanted to have 3 of the 5 books, okay, and I wanted to put them in a particular order, okay. Well, what I could do is, again, I can use my little dashes, right, that I've been using, and I can say, okay, well, if I have a sequence of books, I'm going to have 3, I want to choose 3 books. Now, I have 5 to choose from, right? I have 5 books to choose from, but I only want 3. Well, how many books do I get to choose for the position 1? Well, I have 5, right? One of the 5 is going to be here. And then how many do I have left for the second position? Well, then there's 4, right? And then there's 3. And then the fundamental counting principle just says, hey, if I want to know how many different sequences of 3 books out of 5 that I can get, well, I just multiply these together and I get 60. Okay. Well, guess what? All of these examples where order matters, right? These are permutations. So what I just figured out is the number of permutations of 3 books out of 5 that I can choose from. Now, I did that without the formula, which is right here. So anytime you're dealing with permutations, you can use the strategy that I just showed you, and it'll give you the correct answer every single time. Okay, but just to show you that this does work, just plug in the values here, right? So in the example, what's n? N is the number of items you get to choose from. Okay, so in this case, I have 5 books to choose from, so that's going to be 5 factorial. Now, I'm going to divide by n minus r factorial. What's r? R is the number of books I'm choosing. So this is the number of books I'm choosing from, or the number of books that I have available to choose from. These are the number of books or objects I'm choosing. So on the bottom, in parentheses, it's going to be n minus r, which in my case is going to be 5 minus 3, which is 2. So this is going to end up being 2 factorial. Now, I could go ahead and use my calculator and figure out what 5 factorial is and figure out what 2 factorial is and then divide those. But I could also do this. Watch this. I can write this as 5 times 3 times 2 factorial, right? And divided by 2 factorial. Well, look at this. Since I'm dealing with multiplication, right? Factorial is multiplication, and I'm dividing. Can I cancel across division when I'm multiplying? Absolutely. So can I cancel this number with this number? Absolutely. They're the same, right? So 2 factorial on the top is 2, and divide by 2 factorial on the bottom, which is also 2. So 2 divided by 2 is 1. So now, guess what we get? Oops, I'm sorry. I missed one. Gosh, how did I do that? 4. I missed a 4 here. So we get 5 times 4 times 3 times 2 factorial. So now, look what I got. Didn't I just get the same thing? I got the same thing that I got here using the fundamental counting principle that I got using the formula. So that is why if you use my strategy, use the fundamental counting principle, you will always get the number of permutations. Okay, as long as order matters, and you're talking about sequences of distinct objects where order matters. Okay. Okay. So now, okay, gotta erase this. Oh, let me do this. Can I? Here we go. There we go. Good. So now, much faster. Okay. So here, a teacher wishes to place 5 out of the 8 different books on her shelf. How many arrangements of the 5 books are possible? Well, in this case, again, what would it be? If we think about it, it's going to be what? 8 times 4, 8 times 7 times 6 times 5 times 4, using the fundamental counting principle. Okay? So we set up our dashes. right? So how many books are we choosing? We're choosing 5. 1, 2, 3, 4, 5. Okay, so in each position, we're going to choose one book. So we have 8 to choose from here. We have 7 to choose from here. 6, 5, and 4. And so if we use the fundamental counting principle and multiply, what do we get? Well, all we do is multiply. So 8 times 7 times 6 times 5 times 4 is 6,720. And that's the answer. But if you use the formula, you'll get the exact same answer as well, as you'll see. Okay, so there's our answer, right? And now, if you use now here's the thing. If you use all of them, right? Well, guess what? If you choose all of them, that's the example that we did before with the lining all 8 kids up for the spelling bee. Well, guess what? The permutation formula works for that too. It just turns out to be just n factorial, because what happens in the bottom of our formula here? Well, if it's n, choose n. Well, what's n minus n? 0. We get 0 factorial, which is what? 1. So we get n factorial. Okay, so the formula works in that case too, but so does my strategy. Okay, and my strategy is much easier. So now, let's take a look at this one. Okay, so we want to know the permutation of 3 letters. Okay, so how do we do that? So let's think about this. Okay, so we want to find we want the number of permutations of letters A, B, and C. Okay, so if we want the number of permutations of A, B, and C, which means order matters. So A, B, C is different than C, B, A. And so what do? We treat it exactly the same. Well, how many letters are we choosing? We're choosing all 3 of them, right? Okay. So, and we have how many letters to choose from? 3, A, B, and C. So this is going to be, the answer is going to be 3 factorial. Right? So that should be right, right? So if we do that, then it's going to be 6. The answer is going to be 6, right? Because 3 times 2 times 1 is 6, right? So 3 factorial. And again, that makes sense from our what we've been doing, right? Now, B says, right now, if you want to list out them, I'm not going to list them all, but there's a pattern, right? You can have A, B, C, or you can have A, B, C, or A, C, B, right? You can flip the second 2. Then you can rotate the first one. So then you can have B, C, A, or B, A, C. And then you can rotate again and have C in the first position. And then you have C, A, B, or C, B, A. Okay, so those will give you the 6 outcomes. Okay. Now, what about the number of permutations if just 2 of the letters are to be used? So that means we want only 2 out of the 3, and order matters. So that means we're going to do what? It's going to be 2, right? And we get 3, right, for the first position. And we get 2 choices for the second position. And what do we get? Huh. we get 6 again. Interesting. So we get the same number of permutations. Okay. Now, again, if you look at this, right, you can see why, right? So we can have AB, right, or BA. We can have AC or CA. We can have BC or CB. Well, those give us 6 possible outcomes. And then if you add either C here or B here or C here. So again, if you do A, B, C, you can have A here, right? Or B here or C here. And so you end up with what? The same outcomes. So you can have C with this one or C with this one. You can have B with this one or B with this one. Or A with this one or A with that one. Okay? And so you still get 6. Okay? So now, we want to find the number of permutations of the letters L, M, N, O, P, and Q if just 3 of the letters are used. Okay, so we can use the permutation formula, but again, it'll be a lot easier just to set up your lines. Okay. Oops. So we don't want that one. So we're picking 3, right? We're choosing 3 out of what? Out of the 6 letters. Okay, so how many choices of the letters do I get for the first one? That's going to be 6. How many choices do I get for the second one? 5. And the last one is 4. And so I multiply these together using the fundamental counting principle. And what do I get? I get 130, or excuse me, 120. Right? 6 times 5 is 30. 4 times 30 is 120. Okay, and that's the answer. Okay. Okay. And look at, there's the formula. So the formula, notice how the formula works, right? N factorial over n minus r factorial. Here n is 6. That's the number of items we're choosing from. And how many are we choosing? 3. So it's going to be 6 factorial over 6 minus 3 factorial. And then, of course, you can cancel the 3, 2, 1 with the 3, 2, 1 up here, and you get the same exact answer we got. Now, on your calculator, if you go to math, right? So if you go to your math key, and then you're going to go to your menu, and it's going to be the either probability, it's going to be the probability menu, but it'll, depending on your calculator, it'll either be PRB or PROB. Okay, so either one of those. And then under the probability menu, you just look for the N choose or NPR on your calculator. Okay, and now the thing is on your calculator, you'll have to either put in the number N first, then find NPR, and then enter in your R value, or your calculator will allow you to just fill in some empty boxes. Again, in this case here, they're filling in the empty boxes here. Okay, so on your calculator, it'll look like this: N, P, and then R is the function. Okay, so this is what you look at, and then you're going to use your calculator to find this permutation. So practice using the calculator, using that function. It's pretty quick. Okay, so now you can use my method, which is just the dashes, and then use the fundamental accounting principle. You can use your calculator and use NPR to do it, um, or you could use the formula. Okay. Okay, so now here's an example that says, in how many ways can the letters in the word Tennessee be arranged? How many ways can the letters in the word Tennessee be arranged? Okay, so this is a good one. Okay, well, let's look at this. How many T's are there? There's one T. How many E's are there? There's what? 4 E's, 2 N's, and 2 S's, right? So we need to take that into consideration. Okay, so now this is going to be a little bit different because, see, we're splitting up each letter falls into a different category, right? So the way we need to handle this is going to be using, if we want, what we call distinguishable permutation. Okay, so we have different categories, and each one of these values are different types. Okay, so we want the number of distinguishable permutations. Okay, so in other words, we're treating these as the same, right? So again, distinguishable permutations, which means if I switch this E and this E, well, it's not gonna I'm not gonna notice anything, right? It's gonna be the same. So I want distinguishable permutation. So I need to take each category of letter. Each letter is a different type, right? So what I'm going to do is, well, if I use the fundamental accounting principle, or not if I use the formula is going to be this. I'm going to take n factorial. That's how many letters there are, right? So in this case here, there are how many letters? 9. Okay, so there are n factorial. But now for each category or each type of letter, I have to take that permutation, right? So this is going to be 1t, so there's going to be 1t, so I'm going to do 1 factorial, okay? And then what am I going to do? Oh gosh. Okay, so here's what I'm going to do. So here's 1 factorial, okay? And now I'm going to multiply that bottom one by, well, how many e's are there? Well, there's 4 e's, so I'm going to have 4 factorial. And then how many s's are there? Well, there's 2. So I'm going to have 2 factorial. And then how many n's are there? Well, there's 2 n's. And so I'm going to have another 2 factorial. Okay, so now what this looks like is, well, this I'm going to call n1. This is going to be n2. And this is going to be n3. And then this is going to be n4. Okay, and notice this here, well, what's n? N is going to be 11 in this case. What's n sub 1? 1. N sub 2? 4. And then 2 and 2. Notice that all of these numbers, yep. So all of these numbers add up to 9, which is the number of n, right? So that should always be the case because you're partitioning these letters. So all the letters are being used. So in this case here, what we're going to get is we get 11 factorial, or excuse me, not 11 factorial, 9 factorial. Keep thinking of a different problem. Okay, and then the rest go on the top. And then all I have to do is then take the 9 factorial and then divide by 1 factorial, 4 factorial, 2 factorial, and 2 factorial. Okay, and then just, basically it's going to just be plug and chug. Okay, so if I look at the answer, so here it is, right? So I'm going to use this formula for the distinguishable permutations, and so I get my answer here, which turns out to be 3,780 different distinguishable sequences of those letters. Okay. Okay, so that ends section 8.2, or excuse me, 8.1. So next time we're going to start combinations. Now, what's combinations? Well, combinations are very similar to permutations, except, guess what? Order doesn't matter. Okay. Also, one thing I wanted to mention regarding permutations that wasn't mentioned is that permutations, the formula for permutations, assumes no repeats. Okay. If you allow for repeats, let me go back here. So if you allow for repeats for this one, if you allow for repeats, this just reduces to n to the r power. Because all you're doing is whatever n is, however many numbers you're choosing from, is just repeated over and over again. And the fundamental counting principle just gives you n to the r power. Okay, so in all of those cases where I said, hey, they repeats like the 4-digit access code. Okay, so we just had 10, 10, 10, 10. Well, that's using the formula. So if repeats are allowed, this formula just becomes n to the r. Okay, but again, this formula assumes no repeated characters. Okay, so again, just one more thing to be aware of. Okay, so that ends this section, and next time we'll talk about combinations, which means that, hey, what if order doesn't matter? How does that affect our results? You'll see next time. Take care. Bye-bye.